Okay, I'm going to start sharing my screen so that I can start going over the slides. Thomas, I'm going to get started. Is that okay?
Yep, go for it.
Okay. Okay, welcome everybody to the 2021 edition of Next Generation Electrochemistry. This is a program that has been running now for 6 years. Every summer, it's a summer workshop on the frontiers of electrochemistry. We run it out of the University of Illinois Chicago, and my name is Jordi Cabana. I'm the director of the program. This program is funded by the National Science Foundation, and the Electrochemical Society is our sponsor. A quick overview of what we're doing in the program. I'll show abbreviated versions of this in the subsequent panels, but this is the first one, so I wanted to make sure that everybody is on the right wavelength to have a good discussion. We are online only. We're running for 3 days until Wednesday. We're going to have 9 events in these 3 days. If you joined us last year, this is a significant increase from last year. It's over twice as many events. We're running every event for 90 minutes, and every day the events start at the same time, 10 a.m., which is now, 1 p.m., and 3 p.m. Chicago time. Our official time is the time of UIC. Most events are going to be panel discussions, just like last year. There's going to be one Q&A event tomorrow. And most of the panels are going to be discussions about research topics, except for 2. One of them is going to be about advice in publishing in electrochemistry, for those of you that are in the part of your career where publishing is important. And we'll have a discussion to close the event on careers in electrochemistry. What's next? If you're starting in your career in electrochemistry, what can you do once you have to take the next step? If you are in this Zoom call and you don't have the information to join these 9 events, please contact Thomas, and you should have his contact information if you're in the Zoom call. The panels that are on research discussions are meant to be that. They're meant to be discussion driven by the panelists, but not only by the panelists. The panelists are experts in the domain topic that we're going to be discussing. They will start by giving you a 5-minute opening statement, an opening salvo of what they think are the most important fundamental questions related to the topic that we're discussing in any kind of way, but centered around the idea of electrochemical science. This is an electrochemistry program, and so we're really interested in ways that electrochemistry can evolve in the coming decade. After that opening salvo, there's going to be discussion. The panelists will discuss with each other, but we have a selected group of around 40 students and postdocs in the Zoom call, and we want them to also participate in the discussion live. And they're going to be instructed to throw questions at the panelists as we go. Like I said, we're live streaming on YouTube. Hopefully, those of you that are on YouTube are able to follow these easily. Otherwise, ping us and we'll try to fix it. We have 90 minutes, so we're going to run until 11:30 a.m. Chicago time, because everybody's time is precious. Zoom won't kick us out, so if we see that we run a little longer, I won't kick everybody out at that time. But know that our official end is at 11:30, and my experience from last year is that we'll end around that time. For those of you that are our discussion panelists, aka our NGenE faculty, what I need from you is to be very bold in the way that you present the topics. We want to know what's next. And so that's what I call the frontiers. We are perfectly happy if you want to be controversial in the way that you present the topics, that you want to give people things to think about or ways to think about things differently. You are here influencing people beyond your group. There's a next generation of scientists in the call, and so this is your opportunity to get your ideas to pervade beyond what you do every day. I would love it if you peppered in some examples of how to think critically. but also if you made sure that we focus on the topic of basic electrochemistry, of fundamental electrochemistry, as we discuss applications and other topics. For those of you that are attending, we don't want you to be passive. One of the most important tenets of NGenE is that the students, the attendees, are very strongly involved, and that if possible, don't let the panelists be the ones that are saying whatever they want without having any kind of challenge. We want you to question the status quo, to ask, well, why are we doing these things this way? But that will be after the opening statements. In the meantime, mute your mics, because that way there's no background noise that distracts the discussion. The way that we're going to allow you to question the panelists or to add comments is that whenever you're ready, you should post in the chat something like, I have a question. My preference is that I give you the floor, and you then will be able to ask the question yourself, more than me reading your question. I prefer that you talk to the panelists more than me transcribing you. If you prefer that I read the question, you can also indicate that in the chat. That's okay. If possible, reveal yourselves when you ask the question. If you don't have anything presentable and you prefer to stay with the camera off, we understand that too. Don't be afraid to be challenging of the faculty. All of these faculty are used to that. And so assimilating complex ideas sometimes requires that. And this is going to be a very information-heavy event. Absorb as much as you can and use this information to decide what it is that you want to do next. You're going to have to face this question sooner rather than later, given that you're all grad students and postdocs. And so here's your opportunity to see what's coming and decide which way you want to go. All right, so that's my presentation. That's my way of setting the tone. We're going to start with the discussion, with the opening statement by the faculty. Before we open the floor, we had an internal discussion on the order, and we agreed upon a pre-stated order, and I'm going to be calling on the faculty for them to share their thoughts. So the first person that's going to share their thoughts is Iryna Zenyuk from the University of California, Irvine. And Iryna, whenever you want, you can share your screen, and the floor is all yours.
Can you see my slides?
Yes.
All right. Thank you, Jordi, for organizing this event. And I'm pretty excited to be here on this panel. And I have prepared a few slides, kind of big picture slides, but I'll also focus on electrochemistry and its role in kind of decarbonization and also transforming thermochemistry sectors. So let's look at what are those thermochemical processes currently that are pretty large scale and that we really need to decarbonize. So we need to think about alternative ways to make, for example, steel, cement, hydrogen currently made 99% through steam methane reforming, and of course, ammonia production through Haber-Bosch processes. And for example, if you look at the making of steel, you have, this is a large industrial process, consumes about 8% of energy worldwide. And you start with iron ore, and then you have to reduce it, and typically you use coke. So in this process, you produce CO2, and then you reduce iron ore to iron. Very energy intensive process, emits tons of CO2. So recently, for example, there have been quite nice advances in how to substitute coke for something else. So you can use carbon monoxide and hydrogen, for example, to reduce iron. You can use hydrogen, or you can use electrowinning or electrolysis process. And look at these processes. You need hydrogen, for example, in this step, or you need carbon monoxide and hydrogen. And again, the question is, how do you produce them cleanly? And that's where electrochemistry come into place. You can use electrolysis, and in that way, you can use electricity to split water to produce hydrogen. So looking in every sector here, you can decarbonize the sectors, you can transform them from high temperature thermochemical process into low temperature electrochemical process. My group has a project on looking at making cement, transforming calcium carbonate into calcium hydroxide using electrolysis. And if you look at the large-scale industrial processes that are already electrochemical, it's worthwhile to study them because they already achieved the scale needed to kind of gigawatt scale. And a chloralkali process is electrolysis process that one of the most kind of developed. So you produce chlorine gas and caustic soda, and you use this large-scale hundreds of megawatt scale electrolyzers to do so. And aluminum electrowinning process is another electrochemical process to produce aluminum. So in terms of challenges that we need to look at that are not yet resolved, and that's where they still rely on thermochemistry as combustion, for example, and that's where electrochemistry is still uncertain how to address them. Because if you think about light duty vehicle sector or some other residential heating, you can put batteries, you can use inductive heating for residential buildings. You can use batteries will dominate, already dominating light duty electric vehicles. If you think about California, by 2035, we pledged, Governor Newsom pledged to get rid of internal combustion engines completely. So we are transforming our transportation completely to battery electric vehicles. And those type of sectors will be dominated by batteries. So batteries will electrify anything you can think of, besides some difficult to decarbonize sectors such as chemical industry, and also, for example, long duration grid energy storage. That's where we're thinking other solutions, other electrochemical solutions might be more viable, such as chemical fuels, also hydrogen. And looking to shipping industry, the shipping is also a quite heavy duty industry, and that's where you either need some very large efficient energy dense batteries, or that's again chemical fuels. Well, ammonia or hydrogen can be used as fuel in the electrochemical process, converting to electricity through fuel cells. Aviation, that's another question, because sure, light duty aviation can be transformed through batteries, but more heavy duty long duration flights probably will not be. So we need to know new clean fuels, or we need to look into electrochemical solutions and heavy duty transportations. That's where the sector that we also traditionally thermochemistry in terms of combustion is dominating still, but it's a heavy emitter of CO2, and batteries will play a big portion of it, but there again room for other electrochemical processes. So in terms of for next generation electrochemists, you can think of, yes, we can use inductive heating and cheap electricity for renewable electricity from solar wind to run the existing processes at high temperature, high pressure, and still emit CO2, and then use either negative emission technologies to either store or reduce the CO2 into value-added products. Or alternatively, as electrochemists, I challenge you to reinvent these processes. Think how to make these processes more clean, how to decarbonize this industrial processes using electrochemistry. So you have to reinvent everything from zero, and this is extremely challenging process to do, but as young electrochemists, you still have time. And because the goal is to not only essentially use electricity to run this process, but also to decarbonize them. How can you run them without CO2 emissions? So next slide, just to give you an idea of hydrogen economy that has been talked about a lot. So hydrogen can be used as a fuel and as a chemical feedstock for chemical manufacturing. So that's a large industry. Currently, hydrogen is produced in steam methane reforming process, which emits CO2. And so 99% of hydrogen you see, it's so-called gray hydrogen. You can make it blue hydrogen if you store CO2, for example, in underground caverns, or you can build a pipeline to store CO2. And if you look at the more renewable method of making hydrogen is to using renewable energy, and then use electrolyzers, which are electrochemical devices that transform electricity into hydrogen. You can transport hydrogen through either natural gas pipelines, or you build a hydrogen pipeline network, or liquefy it, and you can store it in underground salt caverns. For example, Utah has those. And then use hydrogen in chemical manufacturing. So it's already used, but it's the fact that we are emitting so much CO2 in steam methane reforming, that's kind of disturbing. So if we can do that in clean way, produce hydrogen with no CO2 emissions, we can significantly transform and decarbonize chemical manufacturing industry, and also the transportation sector in terms of heavy duty vehicles. Lastly, if you haven't read yet, I urge you to read the National Academy of Sciences, Engineering and Medicine recent report on accelerated decarbonization of US energy systems. So this is the report that came out by NASAM just in December 2020, I believe, and they are looking into how to reduce CO2 emissions to zero by 2050. And if you look at the Biden's pledge, this happened in April, just last April, you can see that Biden's pledge kind of overlays very nicely onto this projection that NASAM report built. And Biden's pledge is to reduce 50% reduction in greenhouse gas emissions by 2030 from where we were in 2005. So if you extend this pledge to 2050, we kind of we are where NASAM recommends us to be. So and this is decarbonization will not happen without electrochemical technologies. And if you look at the some of the recommendations the NASAM report produces, it's first of all producing carbon-free electricity. I think that's already we're doing very well with solar and wind, depending where you are in the country. In California, we're mostly solar. If you're in Midwest, you're wind. So electrifying energy services in transportation, buildings, and industry. So that's what this panel, that's what we're trying to do here. We want to electrify our chemical industry. And again, electrochemistry will play a big role in that. And I'm really looking forward to this panel discussion and sharing some more thoughts with you.
All right, thank you, Iryna. Next in our opening statement is Karthish Mathiram from MIT. Karthish, whenever you want.
Excellent. All right. Well, thanks, Jordi, for bringing us all together here. So I think Iryna's done a great job just mentioning and talking about the desire to decarbonize and ways in which we want to make that happen. And I think in that context, I want to try to articulate maybe one paradigm that could perhaps play a role in helping to bring about some of that decarbonization. So we could state a paradigm in which our desire is to start with just CO2, nitrogen, and water, as well as renewable electricity, and to use just those feedstocks to try to synthesize diverse chemicals and materials. And so what this might look like is starting with N2, reducing that with renewable electricity and water, making that into ammonia, taking CO2 and water, converting those into CO and ethylene, and then learning how to react together these first production products, ammonia, CO, and ethylene, with chemistries like oxygen atom transfer to make even more complex molecules, to be able to make ethylene glycol, ethylene oxide, lactones, and amino acids. These are a handful of early stage targets that I think are compelling and in which we've been working in our own lab in terms of being able to make. And so there's several different pieces here that I've already mentioned. The first being able to make nitrogen and water into ammonia. This is certainly a very difficult chemistry just because the nitrogen triple bond is so strong. But we know that virtually all of the nitrogen atoms that we make in synthetic chemicals come from this ammonia that is derived from Haber-Bosch. So if we can decarbonize the manufacturing of ammonia, that decarbonization will then be inherited by many downstream chemicals. So it's really important to decarbonize ammonia production. Today, of course, we make this with temperature and pressure, and that's something that I'll mention in the next slide in terms of thinking from a thermodynamic perspective, what it means to use voltage instead of temperature and pressure. The next sort of area that I think is important is being able to do CO2 reduction to make carbon scaffolds. So if you look at all these molecules, every single one contains carbon-carbon bonds. And so we need to be able to make C2 scaffolds, C3, C4, C5, et cetera, all these different scaffolds that then appear in downstream products. And beyond that, you'll also see in these molecules that they have oxygen atoms at very particular places. So if you assemble these carbon scaffolds from CO2 reduction, you might then want to install oxygen atoms on these molecules in very particular places. And that's a chemistry that we refer to as oxygen atom transfer, something that I think is really underexplored, but which is critical. So if one looks to the conventional processes that are used to install O atoms, those are generally thermochemical. And if you look here specifically at epoxidation chemistry, this is something that's done starting with ethylene, reacting with O2. And if that were just the reaction of ethylene and oxygen going to ethylene oxide, that would be fine. But it turns out that a lot of that ethylene actually is over-oxidized to make CO2. And so there's this issue with the thermochemical processing that goes beyond just burning hydrocarbons for energy, or in having other sorts of emission sources for making hydrogen. Here, there's actual over-oxidation that needs to be contended with. So we've been working in our own lab on a method by which one can take O atoms from water and place those on olefins in order to make the corresponding epoxide. And there are many sort of associated methods of reactivity where one can take O atoms from water and insert it into a carbon-carbon bond to make a lactone, or into a CH bond to make an alcohol, for instance. So I want to really emphasize that this is a very ideal paradigm. I think we can be very confident in saying that this will not be the way that the world works, even in the ideal future. I think in many ways we're going to continue to use petroleum and find more sustainable ways of processing petroleum, and that's going to play a pretty big role. So I do encourage very much to think outside the confines of this sort of ideal paradigm. So very, very briefly here, I want to talk just about the thermodynamics of replacing pressure with voltage. And I want to do that in the context of reducing nitrogen to make ammonia. So we can look at how we make all the world's ammonia today, thermochemically, temperature on the x-axis and pressure on the y-axis. And the colors that you see here are conversion. And conversion ranges from 0 to 1. If it's 0, it means we're entirely at reactants, so we're still at nitrogen and hydrogen. And if we're in a region which is red, or a conversion of 1, that means we have fully gone to products. So we've gone entirely to ammonia. So one might look at this plot and intuitively want to start at low pressures and low temperatures. And as attractive as that looks from a thermodynamic conversion perspective, we know that there is not reactivity at those conditions from a kinetic perspective. So we have to raise the temperature going up to about 500 degrees centigrade. And at that point, these collisions of nitrogens and hydrogens over a catalyst actually start to become viable. Now the issue is thermodynamics. So here we're in a deep blue region of the plot. So even though these collisions are productive, thermodynamically, the product is now forbidden. And so one is forced then to go to a higher pressure. And at this pressure of around 250 atmospheres, one can actually get to a less than 20% single pass conversion, around a 15% single pass conversion. And that's how we make all the world's ammonia today, is with a process that operates at these relatively harsh conditions. And so we can consider instead using voltage in the place of pressure. That's the only change between the plot on the left-hand side and the plot on the right-hand side, is that pressure has been replaced with voltage. And in doing so, you'll see that this is a variable which allows one to cross equilibrium contours in a much more convenient fashion. With pressure, we are following contours. We're applying more and more pressure, but staying in a similarly blue region. Whereas with voltage, one actually cuts across contours. That is something that's fundamentally different between voltage and pressure. Voltage leads to linear excursions through free energy space, whereas pressure has a logarithmic dependence. So you have diminishing returns. It turns out that voltage helps not just the thermodynamics, it also helps the kinetics. So one could conceivably come back down to a lower temperature. That's something that we've very much been working on developing in our own lab in terms of a lithium-mediated nitrogen reduction process. Now, looking at these plots, one may ask, well, what does this mean for the chemical industry as a whole? Should we electrify everything? And I would actually say that we probably don't want to electrify everything. This is actually a more nuanced question. So this is the fundamental question that I'll end with, which is, should temperature, pressure, or voltage be used to drive a given chemical reaction? There are many different ways of answering this question. One can turn to technoeconomics, and I think that's the most normal way of answering this question, which is to say, if I were to use temperature and pressure, it may cost X dollars per kilogram, but if I were to use voltage, it would cost a different amount, and if it's favorable, great, and if it's not, I won't pursue it. And of course, one has to account for externalities, and there are many other complicated pieces here. We're advocating in part here for early stage processes for which the techno-economics are ill-defined to instead use thermodynamics for this analysis, that there are ways in which one can understand well before a process becomes well-defined and better understood. One can use thermodynamics to distinguish the impact of these driving forces. And with that, I'll go ahead and wrap up, but looking forward to the discussion after this.
Thank you, Karthish. Okay, so we're going to the next panelist, Dan Steingart from Columbia University. Dan, whenever you want, the floor is yours.
Great, thank you. Thank you to Iryna and Karthish for kicking it off. Let me share it correctly here. So I'm very much the old engineer of the group. So Jordi, thanks for having me. I'm actually going to talk about work that I did 15 years ago. Holy cow. After I finished my PhD with Jim Evans at Berkeley, Jim Evans proudly called himself a chemical metallurgist and worked on high temperature and low temperature industrial process electrochemistry. I started a company with him, installing the little doohickeys you see on the left. And I traveled all over the country climbing on very hot or very acidic large-scale electrochemical operations, trying to make them a little bit greener at the time. And a little bit greener at the time still in some cases involved CO2 emissions, but we were looking to capture and prevent some real nasties like fluoride gas emissions. So that's my interest and bias in this area. This hasn't been a part of my academic work over the past decade, but it's been a part of my consulting work, and I'm joining an exciting new effort that I'll plug at the end. So thermal processes versus electrochemistry, to look at it from a process engineering point of view, it's a tale of value and reaction area. And so historically, when I learned thermodynamics in 1998, and Jordi probably the same, the cost of electricity was much greater than the cost of coal. And so an intro mechanical engineering or chemical engineering thermal class said that it's likely a factor of 3, and you figure out your Carnot efficiency, and you're off to the races. Now, electrochemical processes also demand a continuous heterogeneous surface at any point in time to execute the desired oxidation or reduction. In thermochemical processes, you just add heat. Now it's so exciting to be an electrochemist in 2021 because the first statement is now demonstrably false. The cost of electricity is now generally cheaper than that of coal, and it's coming hard for natural gas. And this is just amazing because processes like steel and ammonia can now be justifiably, from a first order analysis, even considered. So that analysis that Karthish brought up, when I was a student, I would probably be failed out of a thermo class for even suggesting it, because electricity was seen as such a valuable thing. And now it's almost the cheapest form of electricity. This inversion is so important. Please do not take it for granted. Please look at it, all of what old textbooks tell you with a critical eye because of this. Now, for the throughput, surface area is generally capitally intensive. So wherever we could throw things in a pot and heat it up, we did in the past, not just because coal was cheap, but because we had a volumetric reaction. Think combustion versus surface area. There's cleverness that we can get around this. Now, like I said, I'm an old man, and we did electrochemistry for long before I was born at scale. And the Hall-Héroult process, invented in 1886 simultaneously by 2 people, Hall and Héroult. So they weren't doing it together, they were competing and doing it separately. But they saw the value of this relatively new thing called electricity and making things that couldn't be made before. And it's important to have this mindset, right? Disruption is allowed. It's hard, but it is allowed. And so this is a Hall-Héroult smelter. This is in Mount Holly, South Carolina. Each one of those rows is a row of pots that are about a line of pots that are about the size of a shipping crate. There are 100 of them in each row. There are 400 here. This is a plant that consumes about 400 megawatts continuously to make aluminum. It's an amazing process. Everyone should have to visit one of these things if you're an electrochemical engineer, to give you a sense of what can be done. Now, why did this need to be invented to make aluminum? Well, if we look at this old-fashioned thing called an Ellingham diagram, we see that aluminum reduction sits over here. And the problem with aluminum reduction is that it requires temperatures, if we're using coal as a feedstock, which is what we do now still for steel, to go to temperatures where we're really close to the vaporization temperature of the resultant molten aluminum. So we would reduce the aluminum oxide only to get aluminum vapor, which frankly is really hard and dangerous to capture. And so because of this, aluminum was more expensive than silver until the Hall-Héroult process, and was considered fine dining, and now we use it for our soda cans. And so what's going on here? What does this look like? Well, we're still consuming carbon in this process, if you're not familiar with it. And so this is consumed carbon, and Alcoa and Alcan have a process now that will hopefully get rid of the consumed carbon and just evolve oxygen, but we make CO2. And so what I was working on is a way of preventing this bad thing from happening. The CO2, right, this is a large-scale process, can cover the entire anode. And when it covers the entire anode, remember, we're shoving 400 megawatts through this line of systems, and the voltage is going to do whatever it's going to do. So it's like a CC step without a CV hold. It's very hard to hold the voltage. It'll just do what it wants to do. This reaction goes to 70 volts. Remember, if you're pushing current through something, something will happen. And so the stuff that came out of here was really nasty. And the problem is that they had no way of telling when this would happen. So my company developed sensors that allowed them to measure the current distribution in each anode and predict when this would happen, so they can then back it off. And we could correlate that just by looking at thermal profile. So I'm not going to talk too much about this. I'm happy to get into it. But my point here is that industrial electrochemistry is not just the reaction area itself, but it's the associated controls and sensors that go with that. And this is what allows industrial electrochemistry to be, I think, at the end of history, more powerful than thermochemistry, because electrons are now cheap. Electrons are easier to control than thermal operations because you effectively can flip a switch. And it's the fact that we have only been using electrons for about 100 years at this scale, a little bit more, versus thousands of years of thermochemistry, that we're biased as engineers towards thermochemistry. We just need to be more thoughtful. We have to invent these processes. These are new stuff. This is your template to work with. And so with that, I'm really excited to announce that starting in August, I'm going to be taking a lead from Columbia to think about how we begin to decarbonize steel. So I'm joining this company that's in Boulder called Electrosteel as its chief scientist, at least for the year. I can't talk too much about the idea because the IP is early, but they've come out of stealth in the last month or so. And so they're hiring. And so if you are a graduating electrochemist that wants to knock out 10% of the world's CO2 emissions, give it a look. Thank you.
All right, Dan, thank you very much. And I did not know that. So piece of news, breaking news, an exclusive we're getting this year. Well, congratulations and best of luck with that new endeavor.
Thanks.
We're going to our last, but not least, certainly, panelist, Marta Hatzell from Georgia Institute of Technology. Marta, the floor is yours.
All right. Thanks, everyone. And really great introduction by everyone and very exciting news. So in terms of, I did follow the rules, but I broke the rules a little bit, but I'll try to be brief because a lot has been covered. But the question that was posed to us was, can electrochemistry replace thermochemistry in industry? And the answer to that is yes. It's actually a really simple answer. But then as a faculty member, of course, we changed the question and asked a different question. Should electrochemistry be used to replace thermochemistry in industry? And what I and my group often think about is, well, we got to think about the process, the complete process, not just the reaction when answering this question. We need to think about reliability rather than, I think that there's an excessive push, and my group does it too in our introductions and in our proposals, to talk about distributed, but we really need to talk about reliability and not just distributed. We need to look at costs, and that should not just include capital costs and operating costs. And we need to really think about what is that electrified and electrochemistry are not the same thing, and are there ways to electrify to get the same benefits of renewable electrons rather than completely going to electrochemistry, and then also discerning where something should be electrified or when something should be electrochemistry. So I did stick to only 2 slides, but when given the flexibility, I realized I made everything very small, so I made it a little bigger. So we're supposed to talk about electrochemistry here, and what I'm showing you here is actually a plot of the power consumption for desalination. And I think that there's a lot of parallels to actually the revolution that we saw around reverse osmosis for seawater desalination, and where we see basically electrified chemical production. In that, yes, I think Karthish highlighted, there's a lot of focus on thermodynamics and kinetics that can guide your decision-making early on right now. But eventually, and hopefully sooner than 30 years, which we saw with desalination, but eventually you get to these points where you get close to that thermodynamic minimum. And then when you start to look at where you can make improvements, and so this is the thermodynamic minimum to separate seawater using a reverse osmosis membrane. And right now, this is 2008, you basically were at the thermodynamic minimum. And so there became this revolution of why even engineer reverse osmosis membranes, because this is the thermodynamic minimum. Here's an impractical amount of energy that you will never be able to go beyond because of entropy production and second law limits. And then you start to think about, here are your real opportunities in terms of engineering. And so I think there's going to be analogs with the chemical production industry that we see in reverse osmosis, and that we're not going to want to focus too much on moving thermodynamics and kinetics into this impractical region. And we need to think about what are the future opportunities that we can get here. And so when we start to look at these thermochemical systems, you can see they're quite complex. But most importantly, you see that there's going to be most heavily a reactor and a separations device. And so I think that we need to look at the process holistically and look about what are our product purity limits, what's the cost of that separations, and are there ways to electrify that separations as well? And I think that's going to be an emerging direction, and starting to look at both these reactor and separators in tandem rather than waiting till we optimize the reactor and then moving on to the separations. So the other thing that I think we need to think about as electrochemists is when we use this word distributed, oftentimes we think about the Haber-Bosch process. There's 100 of these facilities globally, and it would be nice to make 10,000 or 100,000 facilities to drive the distance between the facilities and their use down. But we also have to think about reliability. And as you can see here, this is the cost of land in the United States. And you can see the cost of land varies greatly. If you're going to implement either CSP or PV with new electrolysis systems, the price of land is going to be very important for developing these systems. And so this also is a driver for whether we should be using heat thermochemical or electrochemical. These are some estimates that my students have made. And we don't have the numbers here, but this is the very dispersed difference in the levelized cost of ethylene from electrolysis cell, just taking into consideration the solar irradiance and the cost of land variability. And so you don't need to be an expert on understanding GIS and geography, but you do have to be flexible in thinking about whether we should be moving towards PV electrolysis or maybe some CSP thermocatalytic routes. And then finally, I think as electrochemists, we need to remember that our prior catalysis scientists did not take into account social costs when developing their technologies. And this is why we have these plots here where we have a significant amount of greenhouse gases associated with each of our chemicals. And that's historically why we see these duck curves. And that's why we ship highly concentrated chemicals today, hundreds of thousands of miles, often putting our safety and the globe's safety at risk. And so electrochemists don't necessarily need to understand all the nuances of social costs, but they do need to talk with the social scientists to understand how they, as electrochemists, can best communicate how effectively their technology are addressing these social costs. And then finally, my last point is that electrified does not always mean electrochemistry. We're seeing this parallels a lot of what we're seeing in the desalination world as well. And there's some really nice work out of many groups, but Minnesota and then also Notre Dame and Case Western, looking at alternatives that can be electrified processes such as plasma catalysis, or just looking at these resonance-based catalysis processes where it's pseudo-electrified, but you're tuning the binding energy to get a more optimal catalysis. And so I just want everyone to remember that there's other ways to electrify processes, especially catalysis, that could allow for better performance as we move forward, which is ultimately what we desire. And so that is all that I have in my slides.
Thank you, Marta. Okay, that's the end of the opening statement. So now we have about 45 minutes for open-ended discussion. And just again, a reminder of the ground rules. Post your question on if you're interested in interrupting the panelists, post on the chat and we'll give you the floor. We want you to be the one talking to the panelists directly. We also have George Crabtree from UIC and Argonne in the call. He's the co-director of the program, and he's going to be part of the discussion as well. So George, if you have questions, feel free to chime in as we develop the discussion. I was taking some notes just to get the discussion started of the things that you've been talking about. And there's been one big theme that you've all touched on has been the idea that you don't just say, well, because electricity now is cheaper than coal, for example, you don't just willy-nilly try to electrify everything. Particularly in terms of driving driving things with potential, which is one of the sub categories that has been discussed. Karthish, you've talked about thinking about thermodynamics. You've also all talked about thinking about the cost in a holistic way. I'm a battery person, and if you learn something in the battery space, is that costs are a complete moving target. And they're primarily lowered, well, first by economies of scale, but there's been small improvement along the way that have chipped at the difficulties that were there 10 years ago. Is there a specific barrier, scientific barrier, that is stopping us from, driving ammonia production with electrochemistry? Is there a very specific question that we're really struggling with in this context? And the floor is yours to comment. You can chime in as you want.
Yeah, I think in the ammonia case, I can maybe comment on that. And and I think there's several on the call here who have a lot of expertise on this. But I think certainly, just conceptually, the strength of the nitrogen triple bond coming in that reaction is something, and the inertness of it is something that certainly makes it difficult. And I think that being said, when one looks at some of the electrochemical processes that are emerging, like lithium-mediated nitrogen reduction, that's a case where we have some degree of mechanistic understanding, but not a lot still. So we still, I think, have many opportunities in terms of understanding why lithium breaks the nitrogen triple bond, how it does that reaction, why is lithium special compared to any other material and its capability there. And so I think there's a lot there in more general terms to develop in terms of being able to have greater fidelity over understanding the mechanism of electrochemical reactions at interfaces. I think while tools for spectroscopic understanding are more developed for gas phase heterogeneous reactions, and while even the calculations in those contexts are of greater fidelity, at electrochemical interfaces, I think both the experiments, the spectroscopic probing, and the calculations tend to be, in general, of lower fidelity. And so that's really an opportunity more than anything else, right? And that I think in the next decade, we will be able to see those methods improve and build in their accuracy to the point where we become more predictive and less explanatory in what we're able to do.
Anybody else wants to add anything to that thought?
So I'd sort of add on the. I mean, I think that just to boost Karthish's statement, aside from being great high impact journal fodder, the ability to use spectroscopic tools to winnow the reactions that you care about. When you put an electron in, particularly to a multivalent species, whether it's nitrogen or carbon, the odds, right? So this is where I have to get over my early training prejudices. The odds of getting what you want are less so than, say, with metal, where you're going to either get metal or an oxide. And so having online spectroscopy, having the ability to turn the reactions off and play with the kinetics is this beautiful new area. And sometimes you can tease it out electrochemically by doing the right linear sweep or CV. And sometimes you want to shine a laser at that surface and then have that feedback into the control loop for the electron. So, or some sort of beam where you're not electrically interrogating the surface, but interrogating it some other way. I think that in addition to just the learning, feeding that into the control loop for telling you that you're getting the species out that you want is ripe for innovation, particularly at the industrial scale. Those of you that study batteries see a lot of these papers, and I'm guilty of publishing them as well, that say, yes, if we only had this way of measuring this when a battery was in use, this would be great, except for the fact that, to Jordi, to your point, it's going to add like $500 to the cost of the pack, and you're just not going to bear that. For industrial processes, this is chump change, and you're allowed to put this on if it gets you your yield. So to Marta's point, really getting in on the OpEx and how the control loop and the increase in the CapEx can make your OpEx cheaper. One of the hypotheses that I've been playing around in my head is that CapEx rather is like non-recurring engineering. As long as your throughput is efficient, you can bear more of it up front. What I would add in terms of the cost function, and this is really echoing and building on what Marta said, is that the area dependence of electrochemistry is a limitation right now in terms of cost, at least for solid production and metal production. But there's this beautiful and wacky process called fluidized bed electrowinners, or just basically fluidized beds, where you can grow metals like foams and have them roll over one another. And this is really hard stuff. It's where physics meets chemistry, because you basically have this rolling reactive bed, and wet particle flow is still one of the explained rather than understood aspects of fluid dynamics and complex rheology. And so you take reactions that people don't really understand with flow mechanisms that people really don't understand, and you've got some really fun and hairy PhD problems to dig in on that, if you solve, will have enormous impact on industrial processes. So finally to Jordi's point, the cost moves so much because this area is so underexplored that it's ripe for micro disruptions that can really push things forward in such exciting ways.
Any thoughts to be added to that?
Just one, I have a question, because in the ammonia world, it seems like most of the lithium and metal mediated routes have gotten the best performance. Are there, and one thing that you saw with like the Haber-Bosch process is once they came up with the reaction, it was scaled pretty quickly, right? Like within a year, like of the patent to being filed, you know, the benchtop. And so my question is are there any, and I think that there are, but are there any, because I think there's a lot to be learned from startup companies, like is I guess what I'm trying to say. Are there any startup companies that have, you know, been publishing or presenting on the feasibility of that approach? And this is to anyone who's in this field.
I know there have been a handful who have created companies that are looking at sort of these next generation ammonia synthesis methods. For lithium mediated specifically, I'm not aware of one right now. And I'd say in many ways, like the reaction seems to still have a pretty high degree of risk in terms of you know, overcoming, for instance, the relatively low energy efficiency. We were doing cartwheels and somersaults when we hit like a 2% energy efficiency. And that's really great for that reaction to be able to do that. But it's obviously like an order of magnitude below what it needs to be commercially viable. I think there's a pathway there. There are very specific things that need to be done to do that, but it may still, in my view, be in the realm of academic research. And that is a statement that I hope will change in a couple-year time frame.
Yeah, and I only asked that question just because broadly with all of these, I think, and for the students on board, like there is aspect of these startup companies that you don't have that can add to literature and add to accelerating the pace of things as well. And so that's just one thing that you know, is another avenue to help develop the chemical industry. And as I guess Dan will find out.
Yeah, so I mean, you know, metal is so easy compared to nitrogen. So so you're both far braver than I am. I guess you know, another company that spun out of my lab went through this process. You know, just to plug for all the students there. If you're interested in this area, you should definitely check out this program called Activate, which is basically doing an industrial postdoc / startup thing. Where you get to ask questions like this with a group of like-minded people. Activate funded this company called Nitricity that seemed to start with a lithium-mediated approach, but they might have changed. I don't know if anyone knows or can speak to what they might be working on now.
I think they're on the plasma front now, so I think there's...
Got it, okay, yeah. Okay. Well, so here's a loaded question. Is plasma just electrochemistry with gas?
I love these sort of definitions they can become very controversial quickly.
I'm going to start turning the floor because we've accumulated some questions from the students and postdocs in the audience, and I'd like to give them the voice. So I made a list of the order, and I have Arti as the first one in my list. Arti, do you want to unmute yourself and ask your question directly, live?
Yeah. Hi, I hope you can hear me. Thanks a lot for this floor to be able to ask such questions to all these professors. And I have a very broad question. I recently heard about storing CO2 within the Earth's crust in some layer which are packed enough. And I was wondering, is that really a good idea, or we are just delaying the challenge that we should face to our future generations, like the past did by emitting a lot of CO2 into the air, and now we are having a lot of issues with that. So, what is your say on that? That's one of my questions.
I can attempt to answer it, Arti. So if you look at the technologies that we need to decarbonize currently, those difficult to decarbonize technologies such as I mentioned, steel, cement, production, Haber-Bosch process. If you look at this NASA report, by 2050, they project that even by 2030 that we will not be able to decarbonize them, so they will still be emitting a lot of CO2. So so we will have to rely on negative emission technologies, and so storing CO2 will be one of the ways to essentially make sure they're zero emissions. So if you look in the NASM report, they show how the CO2 infrastructure will be built between these caverns where you can store CO2. There will be pipelines, network of CO2 pipelines that can transport CO2 around. So although optimistically, I would love to see this industry to be decarbonized by 2050, but practically because of the cost constraints and because of technology so mature and it takes time to develop new technologies, I still think we might not be able to decarbonize them even by 2050. So so your question is valid. Are we really putting the burden on next generations? And that's kind of question we should be all thinking about, and also think about question of just transition. Are we also putting burden on underrepresented communities that really have carried so far the heaviest burden on the air pollution, on the, if you look at the ports and that emit a lot of various pollutants, that's where the kind of underrepresented communities live, and that's their health affected the most. So if you so just to, I guess, to wrap up my answer, it's a really good question, and we should all think about it, but we probably will be storing CO2 regardless how fast we are trying to decarbonize all this industry.
Would that be a motivation to accelerate the transformation of CO2 electrochemically, so that you don't have to store it, basically?
That's a really I think we have colleagues here who do to work heavily on CO2 reduction that can answer that question, and I think we will be storing it locally or transporting through the pipelines, just to point of where it can be reduced into value-added products.
Yeah, I mean, it's just to chime in, the mass is astonishing, and I think that as electrochemists and people that normally mass and volume normalize things, we don't think about size enough. And so I'm going to harp on this until you boot me from the Zoom, Jordi. But like there was this great review paper or perspective in Nature, late 2019, out of the UK, a lot of authors that looked at the techno-economics of just this question of where is carbon storage at, and the banner number is 17 gigatons. So 17 gigatons of stuff, of carbon dioxide, has to be tethered to mass that is generally the same weight as that molecule. So you're looking at 30 to 40 gigatons per year that have to be captured, which is a daunting number. Right? To give you a sense, there's on the order of 1 gigaton of steel made every year, and that's by far the largest engineering component. Like the US alone makes, from primary production, 30 to 40 megatons of steel, and as you know, we're in the small minority production now. So when you think about specialty products for carbon dioxide, right, there's only so much, even if you think of concrete as a specialty product, we don't need 30 gigatons of concrete, right? Like this is the challenge. There's so much of it that's being put out. So putting it in the Earth's crust, and I say this unfortunately, is almost all we can do right now, because we don't know where else to put it, because these value-added processes have not been developed yet. And we've never had to handle this amount of effluence on a yearly basis ever, right? This is the sobering point of the challenge to me. I think that you have to be able to capture this as a solid and put it somewhere that no one cares about. And so what idea has been floating around, and I've written a bunch of proposals that have been rejected on this, so maybe one of you knows a program manager and sneak me in. But basically the idea is that you just capture the carbon dioxide somehow, electrochemically or shove it against a alkali something and sink it to the bottom of the ocean. Because if you do that, bottom of the ocean's awfully big, and you can begin to rebuild coral reefs. This is a net cost, right? Like we value long-term from coral reefs, not short-term. But I have a hard time thinking what else we're going to do with 17 gigatons plus of mass per year. And I agree that just shoving it underground feels like kicking the can down the road. We're going to have to do some of it. It's awful. Your forebears have failed you in this regard. I'm sorry that we have to do this, but we have to do it for a little bit, and then we have to figure out something else like right quick. And coral reefs seem to be right up there with what we can be doing.
All right. Daunting but hopeful. That's good. And coral reefs coming back, I think that everybody would agree to that. Okay, I have Joy next in my list. You typed the question, but I'm going to give you the floor unless you prefer that I read it.
Thanks. Yeah, I can ask the question.
Sure.
Yeah, so I wanted to ask about decarbonization along with electrification, because as Dan was mentioning, a lot of the reactions that we want to do are super large scale, and a lot of them are reductive in nature. And so I'm asking about how do we think about the anode and how to make that part sustainable, because often we talk about maybe evolving oxygen at the anode, but the reactant that you need for that is water, and stoichiometrically would be pure water. And that's also a scarce resource. So when we think about sustainability and social justice and the scale of all of these reactions, I'm just wondering if you can comment on maybe ideal other value added reactions that could be at the same scale as what we want to do, or how we would get that water. Thank you.
So if you look into, for example, electrolysis, if you think about 1 kilogram of hydrogen gas in energy amounts to about 1 gallon of gasoline. And how much water does it require? It requires around 2 to 3 gallons of water to produce 1 kilogram of hydrogen through water electrolysis. So as you mentioned on the anode, we're feeding water. Essentially, if we look into how much water we already require for a petroleum production to produce equivalent amount of hydrogen, that's pretty much the same amount we will need. So we already use a lot of water for producing some of the extracting fossil fuels, and if we substitute that with electrolysis processes, then that's pretty much same amount of water is needed. So, but it's a good thought, because essentially you have inefficiencies too. So you don't operate electrolyzers at 100% efficiency. Let's say you can have 75% efficiencies, and then you need more water, and it needs to be clean water. So we need balance of plant components. And other alternatives, you can look into chlor-alkali process. They use brine, for example, right, as a feed. So you don't need clean DI water, but then you'll be producing chlorine gas instead of oxygen. So playing with anode reactions, I think that's one of the fun part of electrochemistry, grouping anode and cathode reactions together to find the best thermodynamic potential, but also best kinetics, and also thinking from larger scale availability of resources. That's part of electrochemistry that's very enjoyable, I think.
All right. Let's keep moving through the questions, because I have a relatively long list, and I'd like to give everybody an opportunity. Oyin, go ahead and unmute yourself and ask your question.
Okay, thanks, Jordi. Hi, everyone. My name is Oyin. I'm a PhD candidate at Berkeley, and I have a question. Thank you all for being here today. So for a lot of the basic molecules we've been talking about, for CO2, for example, it can be actually hard to convert these basic molecules to chemicals higher than C1 to C3 products like ethylene, ethanol, and propanol at the high efficiencies and high throughputs that we need at a commercial scale. So rather than speaking of a replacement of thermal processes with electrochemical processes, are there actually viable avenues within the next 5 years for synergy and integration of these electrochemical processes with thermal processes? so that you can put them in series or in tandem, and we can get these higher order hydrocarbons, maybe gasoline one day, chemicals and materials that we can actually incorporate into our existing infrastructure.
I think that's great, and there's a lot of growing focus on hybrid, maybe biocatalysis with electric catalysis with thermocatalysis, maybe all bio, electro, and photo. From what I've seen, there's some really, actually even bio with thermo has some really interesting opportunities. But the key is sometimes the complexity of the system can limit it. But there's also a nice example of this that is in the out of Minnesota, actually, where they've actually tried to use a new absorption separations actually to bring down the temperature of their Haber-Bosch process. And I think that's like one of a good example of like hybridizing technology to reduce kind of some of the load that you don't want with the thermocatalysis. And so I think you're bringing up a really good point, and I think there's a lot of opportunities there.
All right. Next in the queue that I have is Aditya, who's having some issues with his microphone. So he posted on the chat, and I'm just going to read it. Some of the reactants that were mentioned in the presentations generally are not very soluble in aqueous electrochemical systems, and there are mass transfer enhancing electrode assemblies to work around that. Do you think we are near overcoming these limits to compete with the state-of-the-art thermocatalysis processes? Who wants to attack that?
So it's a question on solubility, Jordi?
Yes, it seems that way.
Okay.
You know, the way that I would understand it is if you want to transform something like nitrogen or CO2 in an electrochemical cell, you know, you're going to have to get that gas onto the surface, right? And from fuel cells, how hard that is.
So I'll just go back to the Hall-Héroult process. So aluminum, it would be wonderful if we could get aluminum to work at low temperature or in water, and boy, have people tried to do that. But cryolite, which is 600 degrees, is very effective. And so this is my own ignorance, so I'll kick this onto the nitrogen mafia on the call. But if what does 500 to 600 centigrade electrochemistry allow that aqueous does not for nitrogen? I know it helps, but and it certainly helps on the anode for generating oxygen. You can do that all day long at that temperature range. I'm curious what you all think of that.
Well, I can say we did some side projects on it and have not published.
Okay.
So I can see, I can tell you that one of the problems obviously is ammonia decomposition, and that's a challenge. But there are some interesting opportunities with again, electrified higher temperature, not necessarily electrochemical, but ammonia oxidation is a challenge, and you have the same low temperature challenges with it's actually, we're not limited by the solubility of nitrogen yet with our electrochemistry. That's right, Karthish, right? Are we a little bit, are you guys at that limit? Mass transport?
Yeah, so I think some of the architectures that have been developed for nitrogen reduction now allow us to overcome the sort of transport limits that we were otherwise reaching. So the lithium media chemistry can actually hit transport limits, which is just because of the rates that it operates at. But we're still only operating around a partial current of 10 milliamps per centimeter squared. So if we wanted to be commercial, we probably need to be 1 to 2 orders of magnitude higher than that. And so by the time one gets to those sort of operating conditions, one would, again, I think, be mass transport limited. So a lot of room for new architectural innovation. I think in many ways we kind of borrow the architectures today that we use for fuel cells and electrolyzers, and we hope that they work for chemical manufacturing, electrochemical manufacturing. And I think sort of on-purpose design of new architectures that are made for electrochemical synthesis is really necessary. And there's just a ton to think about in terms of transport there, which is great. Yeah.
So I would like to add to that, if you look at the CO2 reduction, actually now they are moving into the electrolyzers, like similar to water electrolyzers we use, and all the components were borrowed from water electrolyzers. So you see they operate already at 2 amps per centimeter square without mass transfer limitations. This is a question of how do you design gas diffusion electrodes, right, for the specific application. So playing with hydrophobicity, hydrophilicity. Karthish, you had a nice paper on this for ammonia. But to add to that, we run into some of the solubility limitations. When you think about novel electrochemical processes, we have a project on cement, making cement electrochemically. You have to convert calcium carbonate into calcium hydroxide in the electrolysis process, and we are limited by calcium carbonate solubility. It improves with lowering pH, so dissolving it in acid helps. Temperature doesn't help, so it has to be a low temperature process, and we're still pretty much, that's a limitation for larger scale deployment of this type of new electrochemical technology.
I have Wessel next in my list. Wessel, do you want to unmute and share your thoughts?
Can you hear me?
Yes.
Yeah. So I had a question regarding the infrastructure and everything. You guys are developing new electrochemical techniques to convert, move away from thermochemistry and everything. And we're talking on scales that are, even a single, steel plant is significant. And we're trying to do this, on a global scale. The big question is, do you guys factor in the cost of, do you have to throw away this infrastructure and design whole new systems, or can you kind of integrate it with the current infrastructure that you may have for like a steel plant or something along the lines of that?
So I have opinions here, so I'll tell you. The reason I became a professor was because I was crawling around these plants and saw them as the best way of dealing with intermittent renewables. And because I think ultimately any electrochemical process, as opposed to a thermochemical process, has a shorter engineering loop to a reversible pathway. And so it's my thought that these processes will enable renewables rather than slow down their penetration. So I'm going to flip your question around and ask the question I wanted to hear. Will this, how does this work with what has to happen? So what has to happen is we have a new renewable infrastructure, and we need something to do with the intermittent electrons at scale. And we need to convert megatons to gigatons of stuff. And when you look at wind intermittency, when you look at solar intermittency, the residential demands are cyclic, and we want to make sure that baseload can handle that. And there's a prime opportunity for these industrial processes to figure out how to fast ramp and fast stop, basically like a stop-start battery in internal combustion engine now, to respond to the pricing signals that make this work. There's historical precedent for this. When you look at the original growth in aluminum smelters, it was near hydroelectric along the border with Canada, and then after the Depression, or during the Depression, along the TVA, right? So these types of plants anchor new infrastructure. So I think getting them done will actually enable new infrastructure. There's going to be huge capital costs, and we have to commit to it. Current administration seems to be giving the wind behind our back. Let's take as much advantage of it as we can, and make sure that culturally we want to push this forward, because it's going to take more than 4 years. It's going to be at least a decade. But I think this is enabling technology.
I would like to add to that, Jordi, if I can.
Yeah, go ahead.
In terms of so there are stages you can transform the technology completely to new technology. You can use existing technology and change one small part of the process. Like in my slides, I was showing, if you substitute coke for other reducing agent, for example, hydrogen or oxygen or carbon monoxide and hydrogen, this can be done relatively within the same steel making plant. You don't have to change things much. You just have to substitute one component for another, and then you reduce CO2 footprint significantly. If you think, for example, at other like turbines that burn natural gas, right? If you substitute hydrogen for natural gas, how much things you need to change, how much infrastructure you need to change. You need to change the blades of the turbine because hydrogen is can corrode things and embrittlement and all of that. But that's the only thing you have to do. And the companies already make them. Siemens make this turbines to work with hydrogen. If you look at the steel process, that's already ThyssenKrupp and other companies already making steel with this other reducing agents.
You know, I'm learning a lot about what's coming, and I didn't realize just how far along some of these things really are. You know, it's really amazing. I have one more question from the audience, two more. Okay. So I am going to give the floor to Michael next. Michael, if you can unmute and ask your question.
Hey, everyone. I have a question that's sort of sparked by something that Marta said. So I'm really kind of intrigued by the consideration of electrifying separation processes. And like, to be totally transparent, I don't know too many separation processes that are electrified. So I guess I'm sort of wondering, what is the state of the art? And, you know, when we think about any advances in electrifying separation, how does this kind of fit in with the current framework? And then what would, you know, like a transformational advance in this field look like?
That's a good question. And I'll actually answer it with, I'm actually hiring two postdocs, by the way, one in nitrogen catalysis and one in CO2 catalysis. But the CO2 catalysis project is heavily integrated separations and catalysis. So in terms of, I would point to Alan Haddon's work out of MIT. There's a couple ways to electrify CO2 separations. And Alan has probably been leading the way in one way, which is to use redox active molecules to tune the affinity of CO2 to bind to a surface. And he has lots of papers on it. And actually, Professor Liu was a postdoc in his lab, is now moving to Johns Hopkins. And she is also leading the way in a lot of active ways to make this actually process, like scaling it up in many ways. And so that's one way. The easier way is actually just to electrochemically make a basic media that is already used as an adsorbent. So you can adsorb CO2 using electrochemical redox medias, or you can absorb using electrochemical base that you produce electrochemically. And then there's a couple groups working on that approach as well. And then you can directly feed, the nice thing about absorption is you can directly feed it into your electrochemical reactor. And then it can easily integrate with direct DAC systems, direct air capture systems, in a nice way. And there's Carbon Engineering, who's really engineering a lot of that direct air capture for CO2. And so I think those are the two primary methods. There are all other people who are looking at different membrane-based processes like ion exchange membranes, because you can play around with capturing. And so there's electrodialysis cells as well. But I'd say that I really look at Alan Haddon and Professor Liu's work.
Yeah. Do you have an opinion on a specific question that is the let's say the gateway to the engineering component or the implementation component? Is there one question that if we could solve, things would be much easier?
Selectivity and stability in when you have other competing gases. So you're going to have NOx and other things that often poison materials and also adsorb to surfaces. And so when you're especially looking at adsorption processes, you have to be able to selectively bind CO2 instead of NOx, and that is, I think, it's parallels a lot with the electrochemistry, electrocatalysis world.
Right. All right. We have one more question, and so we're getting toward the end. I'm going to make sure that she has an opportunity to ask it. Jessica, you had a question on electrochemistry. Go ahead and unmute yourself and ask it.
Hi, everyone. My name is Jessica Rodriguez. I'm a PhD candidate at the University of California, Davis. And my question is more focused on data interpretation. I have been working with CO2 reduction. And I was very intrigued by the paper published by Dr. Mathiram on the Bayesian analysis, data analysis of the Tafel slope. So I think that one of the challenges, at least for CO2 reduction, is how we interpret the data and all the human error that we can put into it, specifically the TOEFL slope, and how that can hinder how further we go into the development of systems. So my question for all the panel is there specific on how we're interpreting the data that we can improve to decrease these human error sources? And this is for general reactions. I'm talking about CO2 reductions, but it could be for the ammonia synthesis, hydrogen evolution, and how we can work to like just mitigate that and improve the way that we're interpreting this to move forward in the development of catalysts.
Yeah, thanks, Jessica, for a really, really great question. I think there are many contexts in which I think humans want to see an outcome, and that can be very have a strong influence on what you end up seeing in a process. So I think like one that hits home here maybe is that we as a community really want to see things electrified, right? So we may be likely to try to electrify some things that shouldn't be, right? That's sort of, I think, one sort of big picture context. While there are many things that should be electrified as well. And I say that as someone who does want to see a lot of things electrified. So I have to remind myself often to kind of wear the hat of someone who might be interested in other ways of doing things. But the context you're mentioning in data analysis is really important too. I think there are many mechanisms that have been studied out there for things like CO2 reduction where TOEFL slopes are measured. And these TOEFL slopes are often given a lot of weight and are thought to be very important in helping to down select mechanistic possibilities. And one comes into those reactions thinking that the TOEFL slope should be 40, 60, 120, it should adopt certain cardinal values. And when one applies the sort of Bayesian statistics method that you described to look at that data as a whole, it becomes clear that these cardinal values don't really exist in CO2 reduction, which I think is very unsettling, right? It throws into doubt many things that have been said in the past, some by our own group or that I've published before as well. And that means that we need to really take stock of which mechanistic features we really believe in and which need to be reevaluated with depth. And I think holistic analysis of data and stepping back and looking at the last 100 papers that have been published to see what that means altogether is one way of kind of taking a pulse on the field and gauging the health of the field.
This is actually a question that goes very much in the heart of the spirit of the program, because, you know, with electrochemistry, one of the things that I always teach in my electrochemistry class is beware of what the current means. You know, just because you're measuring a current doesn't mean that you're doing what you think you're doing. Do you see a specific obstacle when it comes to advancing the research that can do these transformations that has to do with a very common misinterpretation of data beyond what we just talked about in the TOEFL slopes? Any other pitfalls that you want to warn the next generation against?
So this is not as big of a thing as it was a few years ago in the nitrogen world, but really, I don't like when people game around one metric. And maybe I'm not in the battery world, but I make fun of my sister. Like, you know, in the nitrogen fixation, it was all about Faraday efficiency, and you know, if we make no ammonia, we can get, you know, an infinite amount of selectivity, right? Or we make, you know, we run no current through our cell, and we make ammonia. We can get. So I think he is making sure that you balance your metrics and how you and the importance of the balance metrics. So current density and Faraday efficiency, right? Which most people do now. So just think about holistically, like multiple metrics.
Hold on. Are you saying there are papers out there that pass no current and see ammonia production?
No, I'm not saying that.
That sounds really wild.
No, but theoretically, like, and we all ran into this early on, where you just, if you know, before people realize all the contamination issues, you could put very little charge through your cell and still measure ammonia. So anyway,
so this is a question of you know, having the product that you're trying to produce be part of your feedstock. And so of course it's there because it was there from the beginning. Generally what you're.
Well, and just that it's important to, like, you know, if you're designing an electrolysis cell and you have 100% Faraday efficiency, but you're only making nanomoles of ammonia, what's the value in that, right? And so, you know, and so keep that in mind, like 100% Faraday efficiency is maybe not the goal, you know, and so maybe it's 50% Faraday efficiency at 1 amp per centimeter squared, right? And so, that's just something that we in the early part of the nitrogen, it was just Faraday efficiency was like the race course.
Right, interesting. So basically, it's the idea of you know, being a little richer than just one electrochemical experiment and that's it, and then you run with it.
I just want to add to that you will need to meet all the metrics with one cell or one electrolyzer. In our fuel cell field, you build 3 cells, one for mass activity, one for durability, and one for high current density, all the different loadings. And then when you publish Nature paper, you show, oh, we met all the criteria. Yes, so it's 3 different cells with 3 different loadings. Don't do that.
That sounds familiar.
That's familiar. I mean, I think I think it was Karthish who said this early on, like doing a techno-economic analysis to figure out, you know, what the metrics are. I think that electrochemists, basically scientists, should be focused on characterizing and understanding, and that metrics should be based on the doers and people that are putting the product out, and we should, as scientists and as academics, should give the cleanest data possible for them to then put into this. I am a huge fan of what are called levelized cost models, where basically you pick what your output is. It can be electricity, it can be storage, it can be iron, it can be ammonia, and then you come up with a catch-all, purely economic equation for the levelized cost of what your target is, and then the fun part is figuring out how what you've engineered to date performs along that, and then what metrics matter. Because, for example, in energy storage, which is most of what my academic group works on, a decade ago when I started, this concept of round trip efficiency was crucial because batteries are going to be used for arbitrage. And it assumed that solar was always going to be more expensive, and therefore you could not afford to lose a single joule. And now solar is cheaper and we have too much of it. And so the question is not so much round trip efficiency, but what the levelized cost is. Now, the more you want it to be as efficient as possible, but that's not nearly what's so important. To Iryna's point, it's far more about the operations and maintenance. And so if you look at flow batteries, it's not the round trip efficiency that kills flow battery companies. It's the fact that they charge 2% of capital cost per year for maintenance when it's really costing them 7%, and they have to raise venture capital rounds to cover maintenance, not innovation, right? That's not a good business model. And so I know none of you as academic engineers want to think about membranes breaking and pumps failing, but that might be more important than the efficiency metric that you're going after. I spoke about this a couple of years ago at NGenE, and so this is something I think is really important. Focus on the you know, if I do this, then that will happen. Focus on what the cause and effect is. And then with a separate hat, you can do it, but put a separate hat on and say, okay, now that I understand what this cause and effect is, how much should I weight this in the actual metric of the production of whatever species I'm looking for?
Wow, that's a great thought. I love that this question came out last because we're at the 11:30 Chicago time mark, and we're gonna have to leave it here. But this leaves us on a very high note in the context of the program. So you can take from here, you know, try not to obsess too much about publishing the best performance, because that can be gamed. You know, what are you learning from the process? And if you want to really make an impact at the application level, then you have to play the games the way that you've been told by this faculty. You know, be honest about what it all means at the right scale. So we're going to leave it here just to make sure that we stay in the promise of doing 90 minutes. Thank you very much to our 4 panelists, Iryna, Karthish, Dan, and Marta, for being here with us, for sharing their thoughts. Very insightful discussion on a very cutting-edge area. George posted about a workshop that the Department of Energy is running on topics that are related to this. Don't skip NGenE tomorrow to watch this workshop, but go ahead and starting on Thursday, sign up for this workshop. I am signed up to listen to more opinions on this. It's a very big coming area in the field of electrochemistry, big opportunity for the next generation. So you're at the right time to ride this wave. With that, I am going to end this meeting in this event. We'll close until 1 p.m. Chicago time. So we have an hour and a half to munch on everything we've heard. And we'll start at 1 p.m. with a related topic, this one focused on electrocatalysis. So we'll have similar ideas, but from a different perspective from other faculty. So join us for that. And thank you very much again.